Welcome to the PowerPoint on series and parallel circuits. This PowerPoint is going to go over how these circuits values are solved and how to tell the difference between the two different types. Series circuit is there in the diagram. A series circuit is one with only one path from the positive terminal of the battery through the circuit to the negative terminal of the battery. That's how you tell it's a series circuit. The following are the equations we use to solve for resistance in a series circuit. In series, resistance is the sum of each individual resistors. In the diagram below, you see we have three resistors, R1, R2, and R3. R1 is 100 ohms, R2 is 300 ohms, R3 is 50 ohms. In order to solve for all the other values in the circuit, we must find out what our total resistance of the circuit is. And to do this, we just add them. So in this case, we put our equation, R total equals R1 plus R2 plus R3, which ends up being 100 ohms plus 300 ohms plus 50 ohms, which gives us a total resistance of the circuit of 450 ohms. Solving for the current in a circuit requires the following equations. Again, this is Ohm's law. We already know what the voltage in the circuit is, and we just solved for the resistance, our total. So to solve for our total current, which means the total number of electrons going through, we take 9 volts divided by 450 ohms, and we get our total current equal to 0.020 amps. Now, as you remember from your engineering notation prefix PowerPoint and lecture, we have to convert that into engineering notation and then put the prefix in. And we end up with 20 times 10 to the minus third amps, and we substitute milli for the 10 to the minus third, leaving us with I total equals 20 milliamps. Now solving for the other current in the circuit is easy, and this is the trick to series circuits. This is how we solve for everything else in it. Our total current we found on the previous slide was 20 milliamps. Current represents the flow of electrons through the circuit, and since a series circuit has only one path, all the electrons must flow through that path, which means our total current is the same as our current through R1, it's the same as our current through R2, and it is the same as our current through R3. The current's the same in all parts of a series circuit, and this is the key point that helps us to solve for everything else. The next thing we need to solve for in this problem is the voltage drops on each of the different resistors. If we apply Ohm's law to each resistor, we'll get the voltage drops. We know what the current is in each resistor because we just found our total current, and our current through each resistor is the same. So now we have the current and we have the resistance values we had at the beginning of this practice. So now we just take I times R. So VR1 equals IR1 times R1, 20 milliamps times 100 ohms, and we have 2 volts. That's the amount of voltage that is dropping on R1. We do the same thing for VR2, IR2 times R2, which is 20 milliamps times 300 ohms, and that gives us 6 volts. That's the amount of voltage dropping on resistance 2, or R2. And then for VR3, the same thing, IR3 times R3, 20 milliamps times 50 ohms, and we have 1 volt dropping on the last resistor. This brings us to Kirchhoffs Voltage Law for series circuit, and this is a very important law, one you must understand as we go further into circuits. Kirchhoffs Voltage Law states that the algebraic sum of the voltages in a loop equals 0. In this case, we start off with 9 volts, and we subtract 2 volts from VR1 and 6 volts from VR2 and 1 volt from VR3, and we end up with 0 volts. In other words, 9 minus 2 minus 6 minus 1 equals 0. Another way of saying it is the voltage drops on all the resistances will equal our total voltage in the circuit and leave us with 0 volts at ground at the back end of the circuit. Applying Watt's law to solve for the power drops in the circuit, total power can be found using Watt's law. We said that before was power equals I times V. Applying it to the total power, we get I total times V total. Our current total was 20 milliamps, and our battery voltage was 9 volts. When I multiply those together, I get 180 milliwatts. Now I need to find the power drops on each resistor, and it's the same thing. Power equals current times voltage, IR1 times VR1, 20 milliamps times 2 volts gives me 40 milliwatts on my power in resistor 1. My power in resistor 2, or the power drop in resistor 2, is IR2 times VR2, 20 milliamps times 6 volts, 120 milliwatts. Our power drop in R3, same equation, IR3 times VR3, 20 milliamps times 1 volt, and that gives us 20 milliwatts. Now to find our total power, we can add up the power drops in each resistor, and we should get our 180 milliwatts. We have found power total 2 different ways here. If they match, you have absolutely gotten everything right in this whole circuit. It's a check. And when the checks match, it means you've done a box on the circuit. And if you get the power total both ways, you did everything right and you have the right answer. Now we have the review sheet for all the equations we just went over. You should have this sheet in front of you every time you're doing a series circuit until you have these equations memorized. Do not try to do it from memory before you have them memorized. This will take a while, so I expect you to keep this sheet handy. Our equations for total resistance was R1 plus R2 plus R3. Our equations for current total is that current total equals the current in R1, the current in R2, and the current in R3. Our voltage total equals the sum of the voltage drops in each of the resistor. V total equals VR1 plus VR2 plus VR3. Our power total equals the sum of the power drops on each resistor. Power total equals PR1 plus PR2 plus PR3. Plus Ohm's law is always true in every circuit, and Watt's law is always true in every circuit. Parallel circuits are different. They have a different formation than series circuits, and how you tell is a parallel circuit has multiple paths. That means if you're an electron flowing out of the positive side of the battery, you will have choices to make as you go around the circuit. In this case, there will be 3 different choices. Where you have those choices at, those are called nodes, and that'll come in handy later on as we go through series parallel problems. Okay, so how do you know a circuit is parallel? Well, the top end of the resistor, in this case light bulbs, which are acting as our resistors, will be touching, and the bottom end of the resistors, or light bulbs, are touching. That's how you know they're in parallel. Basically, the positive side of the battery touches all the top parts of the resistors, and the negative side of the battery touches all the bottom side of the resistors. This is a parallel circuit. Each resistor, or in this case light bulbs, fills the full battery voltage across it. And this is how your house is wired. To solve for a parallel voltage in a parallel circuit, usually we'll do parallel voltage across the resistors first because it's the trick. In parallel, all the voltages on all the resistors are the same, and they'll equal the total voltage into those parallel resistors. So in this case, our V total, which is our battery, is 9 volts, and that is also the voltage drop on each resistor. V total equals VR1 equals VR2 equals VR3, in this case 9 volts. With the voltage on each resistor, we now have 2 of the 3 different characteristics, so we can solve for the other one. And the other characteristic is current. So how we solve for current in a parallel circuit? We use Ohm's law. I equals V divided by R. So IR1 will equal VR1, which we already know is 9 volts, divided by R1, which is 90 ohms. This gives us 0.100 amps, or 100 milliamps. IR2, same equation, VR2 divided by R2. 9 volts divided by 45 ohms, which gives us 0.200 amps, or 200 milliamps. IR3 equals VR3 divided by R3. This is 9 volts divided by 180 ohms, which equals 0.050 amps, or 50 milliamps. We can solve for our total current 2 different ways. We can use add up the current drops on each of the branches IR1 plus IR2 plus IR3. This should equal I total, which in this case is 100 milliamps plus 200 milliamps plus 50 milliamps equals 350 milliamps. This will also equal the total current if we take our total voltage divided by our total resistance. Parallel resistance equation, this is where it gets hard. Parallel resistance is the most difficult thing in either series or parallel equations. We have an equation that works for every combination of parallel resistors. It's called the reciprocal of the sum of the reciprocals. Most electronic technicians and engineers do not like solving this equation because it requires several parts and you have to take it step by step to get it right. Basically, it's 1 over the reciprocal of each of the resistors. So in this case, our total resistance is 1 over R1 plus 1 over R2 plus 1 over R3 and so forth. I've solved this example we have here. I have the 1 over, and then it's 1 over 90 plus 1 over 45 plus 1 over 180. And then I have to convert those into the decimal fractions. And this is the hard part. So you get 0.0111 plus 0.0222 plus 0.00556. I add up the lower fraction and I get 1 over 0.0389. And I hit the reciprocal button on my calculator and I end up with 25.7 ohms. Now, 25.7 ohms is my total resistance. You need to notice that it is smaller than any of the resistors in the parallel circuit. That's because parallel resistance is like a freeway. If you got one lane, there will be a lot of resistance. If I have more than one lane, my resistance goes down, and so will, and the same is true for an electrical circuit. So the more parallel resistors I have, the less total resistance I will have. We can do a check on our values here by doing a parallel resistance check using our total values. We knew our total voltage was 9 volts, that's our battery voltage, and we solved for our total current earlier and we got 350 milliamps. If I use Ohm's law on the total values, I get a resistor total of 25.7 ohms. You notice this is the exact same value we got on the previous slide. This is a check. Anytime you do these double checks, it's like a box. You 100% know you have the right answer because there's no way for you to get the same value unless you did every part correctly. And that's the cool part about electronics and Ohm's law and Watt's law. Once you get done with these circuits, if you do your checks, you have a guarantee that you've done the problem correctly. Now, because the reciprocal equation for total resistance is difficult, they have two special cases we can use which are much easier equations for solving for total resistance. If I only have two resistors, I can use the product over the sum. This is a very easy equation to do. Usually, if you have a calculator, you'll take R1 times R2, you'll add the R1 plus R2 in your head and divide by that value, and that will get you R total. You have to be careful not to do the whole thing on the calculator because it's very easy to mess this up. You'll think you're doing the right thing, but the calculator will only do what you're telling it to do, not what you think you're telling it to do. But if you take R1 times R2, add R1 and R2 in your head and divide by that value, you'll get your R total. In this case, 12 times 6 is 72, and in my head I know 12 plus 6 is 18. I divide by 18, I get 4 ohms. My R total is 4 ohms. It's much easier to do than the reciprocal equation. The second special case equation is when I have equal resistors. When I have multiple equal resistors in a circuit, I just take the R value of one of the resistors and divide by the number that are in parallel. In the circuit below, we have 3 100 ohm resistors. I take 100 ohms, I divide by 3, I end up with 33.3 ohms. This is a really easy equation. Most of the time you can do this equation in your head. Parallel power equations are just like parallel series equations. Power equals I times V. We've already solved for I and V in each of our different resistors. So we're going to do the same thing. PR1 equals IR1 times VR1. That's 100 milliamps times 9 volts, which gives us 0.900 watts or 900 milliwatts. We apply the same step to PR2, PR3. IR2 times VR2 equals 200 milliamps times 9 volts, which gives us 1.8 watts or 1800 milliwatts. We do the same thing for PR3. IR3 times VR3 equals 50 milliamps times 9 volts. We get 0.450 watts or 450 milliwatts. And our power total, which can be solved two different ways. We can do I total times V total, 350 milliamps times 9 volts. We get 3.15 watts or 3,150 milliwatts. And our check is that in power you can always add the power drops together to get the total power. This is the same in parallel as it is in series. So in this case we add our power drops, 0.9 watts plus 1.8 watts plus 0.45 watts, and we get the same total power, 3.15 watts. Again, this is a box check. We've got the power, total power both ways. They equal, so we know we did all the values correctly. Our parallel circuit equation sheet, just like our series sheet, is one you need to have in front of you every time you're doing a parallel problem. When you decide which sheet to use, again, in series, you have one path. In parallel, the top part of your resistors are connected and the bottom part of your resistors are connected. Once you've decided which one of those it is, pull out the equation sheet and follow the equations until you have them memorized. I've been doing this for 30 years. I have them memorized. It'll take you a while before you have these all down perfectly, so make sure you review the sheet before doing your problems. In this case, voltage total equals VR1 equals VR2 equals VR3, and this is the key and the trick for solving all your parallel problems. The next part, I total, equals the sum of all the current drops. IR1 plus IR2 plus IR3, the current through each branch added together equals your total current. Our resistors, we had three equations. Our first one was the reciprocal of the sum of the reciprocals. This is good for any combination of parallel resistors. If I have two resistors, I can use the simplified product over the sum, R1 times R2 divided by R1 plus R2. And if they're equal, I can just take the R divided by N to get my total resistance. Power total, I just add up my power drops, PR1 plus PR2 plus PR3 equals my power total. And of course, always, Ohm's law and Watt's law are always true in every circuit. You have completed the lesson. Go on to the practice problems. If you have any problems doing your practice problems, come back to the PowerPoint and review the lesson again.